Find the volume for the set of points satisfying z squared less than or equal to r squared less than or equal to 4. And then we have some information about various volumes that we can use. So probably there's going to be spheres, cylinders, or cones involved. So we know it's a volume question, which means there's a geometry type thing going on. So probably what we need to do is start by understanding what this thing is. So it's some kind of a shape. Now, when we stare at this, what do we see? Well, we see z and r. So if we see z and r, that implies that we have to be in cylindrical coordinates. So our shape here is being described via cylindrical coordinates. Now, how do we know that? Well, because the only place where z and r show up together in the same type of coordinate system is when we're dealing with cylindrical coordinates. Now, what's the key with cylindrical coordinates? Well, it's how do we describe our points. And we describe them in terms of z, r, and theta. Now, you might say, hey, there is no theta. Well, what does that mean? Well, that means we have something really cool going on. In other words, if there's no theta, we get this nice rotational symmetry around the z-axis. So whatever our shape is, if we were to spin it around the z-axis, we would see the same thing. So that's a good clue. And in fact, that tells us how we should go about trying to understand what the shape is. So instead of trying to understand it three-dimensionally, we can start by saying, well, let's just look at sort of a slice. And here, by a slice, I really mean like a half plane. So what I'm going to do is I'm going to look at a half plane. Now this is, I fix theta. So in other words, theta is fixed. And remember, after we understand what one fixed theta looks like, we spin it around and we get everything. So what does that half plane look like? Well, what we see is that on the half plane, the edge, that's the z-axis. Then as we come out, it's not x or y, it's simply r. You know, it's how far off the z-axis are we? Because that's how you can think of r. r is distance to z-axis. Okay, so let's take a look at what we have. We have z squared less than or equal to r squared and r squared less than or equal to 4. If we start with the second one, r squared less than or equal to 4. Well, that tells us r has to be less than or equal to 2. Now, technically it tells us that negative 2 less than or equal to r less than or equal to positive 2. But because we think of r as just saying how far we are from the z-axis, we always like to think of r as a positive value. So, that means if I come over here and I draw r equals 2, our region has to lie inside of there somehow. All right. But remember, that's only one of our inequalities. We have a second one. This one that says z squared less than or equal to r squared. Well, if z squared is less than or equal to r squared, then if we take the square root of both sides, and we say, well, the square root of z squared, that's actually absolute value of z, is less than or equal to the square root of r squared, absolute value of r, but again, r is always going to be greater than or equal to 0, so we can just say r. So the absolute value of z is less than or equal to r. Now if you were to graph this, oftentimes say, look, don't worry about the inequality, think about the equality. R equals the absolute value of z. Well, that would be a v turned sideways. So we see this v shape here. This is r equals absolute value of z. Now the question is, where do we fit in? Because there are sort of three parts that we could be. Now, if you're not sure, just sort of go to sort of a very extreme point. Say, okay, if suppose z is very large and r is very small, well, then it can't be that the size of z is less than or equal to r. Similar reasoning down here, that also gets ruled out. But if, say I'm over here, r is very large and z is very small, like 0, no problem. So, we get that the other inequality gives us this region. Now, what's our slice contain? Well, it's where they overlap. So our slice contains that. All right, good. Progress, progress. So we can update our picture now. And coming over here, we say, all right, so if we look at our slice, we see a triangle. And remember, what's going to happen is we're going to spin our slice around. And let's see, when we spin our slice, what do we form? Well, this straight line, when we spin it around the z-axis, is going to end up forming a cylinder. So we get a cylinder. All right. In fact, we can say a little bit more about our cylinder. This radius here corresponds to how far off we are here. So it's 2. The height of our cylinder, well, we're going to go from there to there. Now, because we have that r is the absolute value of z, this distance is 2. This distance is also 2. Total length is 4. Now, that's the outside line. What about the lines coming in? Well, any line that comes into the origin, when you spin it, that's going to form a cone. In general, any line that comes into the z-axis when we spin it forms a cone. And so what we're going to end up with is we actually end up with a pair of cones. So the top line here gives us our top cone, and the bottom line, our bottom cone. So we have now our shape is what? It's a cylinder with 2 cones that have been taken out of top and bottom. So something roughly like that. It's kind of hard to sketch with the missing parts, but that's the philosophy. All right, so cylinder with cones out of top and bottom. Now we can answer the question that we were after, because remember, this was just a stepping stone. We wanted to see what the shape looked like so we could find the volume. So to find the volume, we'll take the volume of the cylinder. All right, so that's going to be height of 4, radius of 2, so the volume of the cylinder. And then we're going to subtract off the volume of the cones. Now the cones are actually the same shape. So I can subtract off 2 of the volumes of just one of them. Okay, so the volume of the cylinder, that's pi r squared, so 2 squared, h, 4, minus 2 times 1/3 pi r squared is 2 squared, and h, remember here, h is the volume of the cone, which is halfway, because the cone only goes halfway, so that's 2. So if you write this out, that's 16 pi minus 16/3 pi, a grand total of 32/3 pi. There you go. That's the answer. Okay, good. Well, what was the key? Understanding what coordinate system we were in. Saying, well, look, if I want to find a volume, first thing is understand the shape. So think about what the shape is. And here, I would say, in general, if you're dealing with objects and you're not sure, look in slices. So a fixed theta is really useful when you're dealing with cylindrical coordinates. All right, good. Now, on to today's material. Well, where are we going? So far what we've learned is we've learned about how to describe where we're at. So we learned about our coordinate systems. Well, good, but we also need one other thing. Not only do we need the ability to describe where we're at, we also need the ability to describe how we change. In other words, as we move through space, how does our change happen? How much change has occurred? How do we describe it? Now, in general, change has 2 important parts. There's the direction of change, and there's the magnitude, which we call the amount, or sometimes it's called the size. Now, we've been spoiled because we've been working with numbers, and numbers can be very flexible in that numbers can also be used to describe both location and change, and because of their great flexibility, things are very simple. But now we have to go up into multiple dimensions, and we're no longer going to have that flexibility. Location and change are going to sort of differentiate into 2 different objects. So you have to be able to work with both. All right, well, so what's the idea? The way we're going to describe our change is with vectors. So these are objects which describe how much things change. Now, how do we think of them? If we're trying to think of them geometrically, we can think of them as sort of an arrow. And the intuition says, I want to say how much I change. So the idea is the tail of the arrow is where you start. The tip of the arrow is where you stop. So that the arrow indicates the distance, or the change, start to stop. So we have many possible things that can happen. Now, here, there's a really important point to make, which is that vectors aren't tied to location. And so here we go. Let's talk about what we mean by that. This is a vector, because I have a start point and a stop point. Now, if I move this vector, but I keep the same angle, or same direction, even though the start and stop point move, the same change has happened, and therefore it's the same vector. So again, vectors aren't tied to locations. I can move this vector any way I want, as long as I keep the change the same. Now if I turn it, that is a different vector, because now the direction has changed. So it's not that the location that matters, it's the change that matters, and that's going to be really important. So as an example, we have a whole bunch of vectors here, but in fact, not quite so many as you might think, because if you look, this vector and this vector, they're actually the same vector. These two are equal to each other. Even though that they're drawn in different locations, they represent the same change, so therefore they're the same vector. Now, if you look at this vector, it has the same direction as the other two. You might call it parallel, but has a different amount of length or different magnitude. So here we think of the amount of change. It's like you pulled out a ruler and you were to measure. So this is not the same vector as that. You also could, of course, reverse direction. You notice these two vectors here, they are different lengths, but they also are sort of the opposite directions. Well, that's okay. They're still considered parallel. So parallel is you're pointing in the same direction, or you are pointing in the exact opposite direction. If we were using degrees still, we would say you would do a complete 180. But of course we're not doing degrees, so we do radians. Okay, so what can we do with vectors? So again, just remember, what are vectors? They're representing change. So what can we do with change? That's the real question. So the first thing we're going to talk about is scaling. So what is scaling? It says, I want to scale. So scale here is we're thinking of changing the length by some multiplicative factor. So as an example, if I have v, twice v is going to be twice as long. And if I have half v, that's half as long. In general, if I have some multiple of v, 5v, 7v, whatever, I'll have 5 copies or 7 copies. It doesn't even have to be a whole number. I can have exotic numbers like pi. Now, if I have a negative I'm going to think of as reversing direction. And in general, this is sort of a nice idea to have in place, which is that negatives are really all about reversing orientation. So positive and negative, what we've been working with for a long time, have actually always been about orientation. Positive goes towards what we call the plus infinity, and negative goes towards the minus infinity. So we've always had this orientation built into our calculus, into our number system. We're just now going to make it a little bit more explicit as we go forward. Okay, so scaling is we multiply the vector by some constant factor, changing the length, possibly reversing the direction. Now, one thing to keep in mind is that the vectors are still going to be parallel. So, in fact, in general, we'll say that two vectors are parallel if I can scale one to get the other. Now, the other thing we can do is we can add vectors. Now, what we mean by adding is we're going to take two different vectors, possibly more than two, but we'll just start with two. And we're going to combine them together by chaining. So, suppose I start at this corner here. That's my start point. And then I place vector u. And now, u says do the change. So after I apply the change, that's my current point. Now, the end of u becomes the start of v. And run that change. And now, the result is I start here. If I do both the change in u and the change in v, so the change in u and the change in v, I'll end up at this point there. So this vector down the middle is u plus v. Now it turns out it doesn't matter which order we do the changes in. So if I run the change of v first and then run the change of u, I'll still end up at the same point. And what we see right here, this is a really important idea, is we see a parallelogram. And these are going to be important as we get into understanding things about size and totals. And we're going to use this idea of parallelograms, especially as we get into the third part of the course, again and again and again. All right, so we've got our geometry. We've got these directed line segments, these arrows, if you will. We can scale them, we can add them, and intuitively they're making sense. However, at some point we have to go from arrows and get to something we can work with. Something we can do algebra with, because we love algebra. I mean, that's why we took calculus, because we were just so infatuated with algebra. We said, hey, I'd like to keep going. And the way we do that is to put numbers on things. So how do we start? Well, the key here is the following. To say, well, look, let's come up with 3 really special vectors. We're going to call these I, J, K. And what they are they're vectors of length 1 that point in very nice directions. So I points in the x direction, J in the y direction, and K in the z direction. Now, in fact, more specifically, I is on the positive x-axis, J is the positive y-axis, and K is the positive z-axis. Now, one of the things that happens is that they sometimes perform double duty. So when you're doing a 2-dimensional problem, you might just use only I and J. In that case, I points in the x direction and J points in the y direction. In 3 dimensions, what happens is now we have I points in the x direction. This is x. So I, J, K. So these vectors, now we have nice vectors pointing in all directions. Well, what's the convenience of having these 3 vectors? Is there anything special about them? And it turns out that there is something nice about these 3 vectors. It's not only true about I, J, and K, but it's very convenient to work with them. And it's the following. Every vector in 3 dimensions can be written as some combination of I, J, and K. So how does that work? So let's think about our vector. We have here a vector that goes from point A to point B. And generally speaking, we call this the vector A, B with an arrow on top. So that indicates start at A, go to B. And suppose I want to write this as some combination of I, J, and K. So in particular, what are we really saying here? Now, linear means that you have multiples and added together. So what I want to do is I want to have some vector that points just in x, combined with some vector that points just in y, and some vector that just points in z. And we say, hey, there's this nice box here. And the box, everything is parallel to the axes or to the nice planes. So what we can do is we can move in the nice ways. So for instance, I can move just in the x direction if I move along that edge. And I say, okay, well, how much did I move? In other words, what was the change? Well, I didn't move in y or z. I only moved in x. And I started here, x was x1. Here, x is x2. So the change was x2 minus x1. That's how much I changed. So this edge is x2 minus x1, I. Now, I move purely in the y direction. This is parallel to the y-axis, so it moves only in y. So that means the x's stayed the same, only the y changed. So what did the y change by? Well, I start at y1 and I ended at y2, so it's y2 minus y1 times j. And finally, I'm going to move purely in the z direction. So again, I'm fixing my x and y. It's only z that changes. I started at z1, I ended at z2, and therefore that's z2 minus z1 times k. So this vector AB, which goes directly between A and B, I can break up as a combination of three vectors. And I say, okay, great. And those three vectors happen to lie along multiples of I, j, and k. So we get the following. So AB, again, x2 minus x1i plus y2 minus y1j plus z2 minus z1k, these three vectors combined. Well, we're going to just simplify this and write this in the shorthand notation as a triple. So we have the change in the x direction, change in the y direction, and change in the z direction. And so we can really think about what's happening here is that my vectors correspond to changes in each direction. So that's what's going on. Now, one of the things you might notice here is our notation. We are using slightly different notation. We're using these angled brackets because vectors aren't points. They represent different things. And so you got to be careful here. The reason vectors and points are different is because points are dependent on our description, on where we're at. And if we change our description of our coordinate system, we change our points. And so we can't have something, well, that is to say it's not invariant. Whereas vectors should be invariant. So you got to be really careful. The moral is just pay attention. Vectors should be vectors and points should be points. By the way, we call this component form, and it really just says break it down, understand what's happening in each direction. So, as an example, find the vector which goes between 2 points. So we pick some points, say 3, -2, pi, 5, 6, and e. So if I want to find the vector, I look at the change. Now, the important thing is vectors go from one point to another point, so you have to understand where's the start, where's the stop. So in this case, here's our start, here's our stop. All right, so if I start at 3 and I end at 5, my change from 3 to 5 would be 5 minus 3, stop minus start. That's 2. I go from -2 to +6. How much should I change by? And the answer is it's 8. Or I could take 6, subtract -2. And if I go from pi to e, my change, well, stop minus start, e minus pi. It's all right that we have strange looking numbers. No problem. So there you go. There's the vector which goes from those points, 2 points together. So now we're feeling a little bit more comfortable because we say, aha, now I have vectors and something I can work with, collections of numbers. And so I want to be able to do everything that was done before. So, okay, what was the things that we were doing before? Well, namely, we had 2 basic rules, scaling and adding. So let's take a look at those in component form. And what we see is that it's really easy to do scaling and adding in component form. Because here's the really simple idea. Things work entry-wise. And by that, we mean, look, just work with each entry. So if I want to scale a vector, say, multiply it by a constant, k times the vector ABC, it's the same as multiplying every entry of the vector by k. So another way to think about it is like, look, if I want to double it, k equals 2. So what I'll do is I'll double each change. So I double the change in x, I double the change in y, and I double the change in z. If I want to add vectors, so I have a vector a, b, c, and I'm going to add it to the vector d, e, f, the way that can be done is say, well, let's look at what happens in each individual component. So we take a and d together, so the change in x plus the second change in x, our change in y's, b and e, and our change in z, c and f. and that will be our new vector. So it's really easy to work with what we had before. Now the other thing we might want to do is we might want to find the magnitude of a vector. Now recall, what's magnitude? Magnitude is length. So before, it was very easy to talk about magnitude of a vector. If I want to find the magnitude of a vector, what I would do is I would say, look, if this is my vector, I'm just going to pull out my ruler and I start measuring. So I pull my ruler out and I say, okay, well, let's see, it's let's see, it's 1, 2, 3, 4, 5. It looks like about 5.6. All right, done, easy. But now we don't say, look, we don't have a ruler. We have a set of numbers. What's the magnitude? What's the length? And the way we understand that is to think about what's going on. So remember, a vector is not tied to a particular point. So we can move the vectors as we need to. So one thing we can do is we can move our vector. Let's say this is the vector here, A, B, C. All right, that's a simple vector. And let's move it so that the tail of the vector is at a convenient location. And the most convenient location for us is 0, 0, 0. It doesn't have to be 0, 0, 0, but that's fine for us. Where do I stop? My start is 0, 0. My change is A, B, C. My stop is at the point A, B, C. All right. Now I can actually say the length of the vector is this distance between the 2 points. So we can apply the distance formula. So the distance formula from the start to the stop gives us that the magnitude of the vector ABC is the square root of a squared plus b squared plus c squared. In general, if you remember the distance formula, so distance was the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Well, that's delta x squared plus delta y squared plus delta z squared. So it's really, the distance is saying how much have you changed. And that's what vectors are measuring. They're measuring change. Now, a little comment here. You might notice our notation looks really familiar. It looks a lot like an absolute value sign. That's not a coincidence. It looks a lot like an absolute value sign because absolute value has always been about measuring size. And here we're trying to measure the size of the vector. If you think about the absolute value of a number, one way to interpret that is how far away is that number from 0. So if here's 0, and I look at 2, well, the absolute value of 2 is how far away you are from 2. So it's 2. If I come over here to negative 3, well, the absolute value of negative 3, that's how far away you are from 0. So it's 3. So absolute value has always been about size. So that's why we use the same notation. Now, depending upon what books you see in the future, or old exams, you might notice that the notation is slightly differently. Sometimes they use 2 bars. That's just different notation. But that's okay. We're adaptable. We can figure out different notation. No problem. No problem. All right. Well, now that we can talk about length of vectors, let's talk about a very special vector, which is a unit vector. Now, even the word, even before we see the definition, read the sentence, if we hear the word unit, we think, oh, wait a second, we've heard unit before, like unit circle is a circle with length 1. So unit vector is a vector with length 1. In general, whenever you see the word unit, you should really think about something with having length 1. Now, the unit circle, I meant to say radius is 1. But this is very common. You'll see this in English, for example. So you have words like unicycle, which means you have something with 1 wheel. You have unibrow, which means like you have 1 eyebrow. Or you have unicorn, which means that there's only 1 piece of corn. So anyways, those are units. All right. Well, why do we care about unit vectors? Well, remember, what do vectors have? Vectors have 2 special properties. They have the direction and the magnitude. So if you take out the magnitude, all that's left is the direction. So unit vectors, we can really think about it, are saying we're just down only to pure direction. So that's why unit vectors are going to be very convenient for us. They're going to stand in for our directions. Now, there is one vector we have to talk about, which is the zero vector. The zero vector, as its name implies, is nothing happened. So it's the vector where there's no change. And this vector has a couple of unique properties. It's the only vector which has length 0, but it's also a vector which has no direction. And I like to call it the art history major of vectors. No direction. But an alternative way is you could say it has every direction. Well, what's right? Well, depends who you ask. I like to say, let's just say directionless for now. Now, suppose I'm not the zero vector, then there's a nice fact. If I'm any vector that's not the zero vector, we can make a unit vector that points in that direction. Now, the key here is to remember that all we need is to make sure it has length 1. So I say, how long is that vector? Well, maybe it's length 2. I say, okay, well, that says that the magnitude is too large. I need to scale, so it's half the current length. So I divide by 1 over its magnitude. If it was length 5, I'd multiply by 1/5. If it was length 1/2, I'd multiply by 1 over 1/2 or 2, and so forth and so on. So by scaling by 1 over the magnitude, I'm adjusting the length to be just right. Just right. We want it to be the Goldilocks of vectors. Not too short, not too long, just right. So I have some examples. Find unit vectors with the same direction as the following vectors. Well, let's start really simple. 3, -4. All right, 2 dimensions. No problem. We can do that. So what do? Well, let's talk about the magnitude of 3, -4. So that would be the square root of 3 squared plus -4 squared, which would be the square root of 9 plus 16, square root of 25, which is 5. So currently, this has length 5. So if I want to make it a unit vector, I need to scale by 1 over the magnitude. So we're going to multiply this by 1/5. So 1/5, 3, -4, and we can leave it like that, or if we're in the mood, we can multiply through 3/5, -4/5. All right, well, okay, that was not so bad. Let's try to kick it up a notch. 3 dimensions. All right, 4, -2, 6. Okay, well, find the length. 4, -2, 6. So that'd be the square root of 4 squared, -2 squared, 6 squared. So that'd be the square root of 16 plus 4 plus 36. All right, let's see. Oh, that's 20. That's square root of 56. Now, if we wanted to, we could be creative. It turns out that 56, that's 4 times 14. I think. Is it? Sure, why not? Okay, so that's 4 times 14. Well, okay, so we can write this as 2 square root of 14. So this becomes 1 over 2 square root of 14 and 4 -2, 6. Well, we could factor out a 2 and say that's 1 over square root of 14 times 2 -1, 3. Now, one of the things that we could have done at the start is we could have actually made our lives easier and said, hey, hold on a second. Before I even start this problem, I know I'm going to scale, so let me just get rid of any common factor. And because I can see that all these numbers were even, one of the things that we could have done at the start is say, well, look, let's not work with that vector. Alternatively, let's work with the vector 2, -1, 3. Because these two point in the same direction. I'm just essentially scaling out a common factor. That would still give us the same unit vector because we'd still end up going in the same direction. Whenever I scale a vector, I haven't changed the direction. And so if you ever have a chance to say, I have to find a vector, a unit vector, one nice thing to make your life easier is scale out common factors first. Well, we have a little bit of space, so let's do one more. Okay, let's find a vector. Let's say 1. Let's say square root of 2t and t squared. Okay, so there's our vector. Now you're probably thinking, wait a second, those aren't numbers, those are symbols. There's t's involved. Is that really a vector? Sure, why not? I mean, a vector is really just a collection of changes, and later on we're going to get into this idea of saying, oh, we could actually have extra things floating around. Like we could have a vector which depends on, say, time. So this is perfectly fine. So what's the magnitude of this vector? Well, 1 square root of 2t squared. That'll be the square root of, well, we square each part, so that's 1. We square this part, square root of 2 squared will be 2. Then that'll become t squared. Then this will become t squared squared. Well, I can write that's t squared squared. And if you look, it's like, whoa, interesting. This is really 1 plus t squared squared. So ultimately you get 1 plus t squared. That's the length. So the unit vector that points in that direction is 1 over 1 plus t squared times 1 square root of 2t and t squared. And again, if we wanted to, we can multiply that through. All right. So finding unit vectors, no problems. No problems. Good. So let's just make a few more comments here. One thing to note is that what you think should be true is often true. In other words, vectors work fairly intuitively. So let's just sort of check our understanding. So I have a vector u, and I add the 0 vector. Now remember, u is representing change. The 0 vector also represents change. It represents the change of nothing happening. So if I take the change in u and I add something that doesn't do any change at all, the result is the change in u. So in other words, adding the 0 vector to something doesn't do anything. On the other hand, if I take the vector u and I add not the 0 vector, but the 0 number, what I get there is actually a little bit interesting because it's nonsense. All right, what does that mean? Well, it means that you can't add vectors and numbers. They're different types of objects. You got to be careful. Pay attention to what's happening. A vector is a vector and a number is a number. They're different types of things. You can't mix them together. So be really careful. All right, how about 0 times a vector in u? Now remember, this is like we're scaling it. And if we think about 0, it says I want to end up with when we scale, we want to sort of change the length. Essentially, we're saying we want to scale it so it has no change. Well, if it's no change, that's going to be the 0 vector. If I take 1 times u, well, that's going to be just u, because it says, really, I want to keep the vector that I currently have. Suppose I take the vector u and I subtract the vector u. Now, what does that mean? It says, look, start at some point, doesn't matter where, change by whatever u tells you to do. Okay. Minus u says now change, but the opposite of u. So if I combine these together, I basically go back and forth. I start and stop at the same point. Start and stop at the same point, that means I get to no change, 0 vector. If I take a plus b, and I use that to scale u, it turns out that this is au plus bu. And that's very simple. You can verify it using component form. Similarly, if I have the vectors u and v combined and I scale by a, that's au plus av. And lastly, if I want to take the magnitude of a times the vector u, what happens? Well, that's the size of a, size of u. So kind of like what absolute value does. The absolute value of the product of two things, you take the absolute value of each part. All right, well, one more idea. The midpoint of 2 points. So if I have the midpoint of x1, y1, z1, and x2, y2, z2, what does that mean? Well, it gives it away. Mid is like middle, the middle point. And so it's that point halfway in between. How do I find that? Now, if we were just dealing with numbers, it's pretty easy. So if I have 2, so here's 2, and let's say here's 8, and I ask, well, what's halfway between 2 and 8? Well, the answer is it's 2 plus 8 divided by 2, which is 5. So the middle of two numbers is 5. But now we have to say, okay, what's happening when we have sort of points in higher dimensions? So I have here x1, y1, z1, and x2, y2, z2. And I want to say, well, what's the point halfway? What's this point? Let's say this is the halfway point. What can we do? Well, let's talk about what we can't do. The first thing is we can't add points. Points don't add because points are dependent on your coordinate system. See, points aren't dependent on space. They're dependent on how you describe your location in space. And because of that, points aren't inherently geometrical. It's only when we are very careful that we can get away with using them. So we can't just add points willy-nilly. So we say, okay, well, if we can't add points, then what do we do? Well, we say, all right, we've been learning about vectors. Let's think about this in terms of vectors. So what we can do is we can say, hey, I can talk about the vector that goes between my 2 points. Now that's perfectly allowed to talk about that vector. So that would be the vector x2 minus x1, y2 minus y1, z2 minus z1. Now, I want a vector that goes to the halfway point. So the vector that goes to the halfway point would be the vector that only goes half as far. So that vector would look something like this. So it would be half x2 minus x1, y2 minus y1, z2 minus z1. So half as far. So now I have this vector gets me from that point to my midpoint. So where's my midpoint at? Well, think about what's happening. Vectors tell me my change. I have my start. So if I have my start, I know my change, I know where I end. So the key here is you can think of it as the following. My midpoint is going to be my start plus my change, 1/2 x2 minus x1. And that's in the x direction. My start plus my change. And finally in the z direction, my start plus my change. All right, so that's the midpoint. Now if we clean this up, we can see, okay, we have x1 minus half x1, that's a half x1. So we get x1 plus x2 over 2, y1 plus y2 over 2, and z1 plus z2 over 2. And there we go. And that's the safe way to do it. Don't add points. Think about it as manipulating vectors, because that's safe. Manipulating vectors is safe. Adding points is a dangerous thing to do. So let's find the midpoint between some points. So it's fairly simple. We just write some numbers in, 2, 3, 5, -7, pi, and 1. So what do? We add each entry. So 2 plus -7, divide by 2. 3 plus pi, divide by 2. 5 plus 1, divide by 2. 2 plus -7, that's -5. So -5 halves. 3 plus pi is 3 plus pi. 5 plus 1 is 6. Divided by 2 is 3. And there you go. Good. All right, one last idea. Suppose A, B, C, D are the vertices of a parallelogram. Now, parallelogram means parallel sides. So, we're going to draw ourselves a parallelogram. And let's hopefully, looks very parallelogram-like. There we go. So we have A, B, C, D. There we go. What do we want? Well, we want to say that the midpoint of A and C, so in other words, if we connected A and C together and looked at the halfway point, it's the same as the midpoint of B and D. So in other words, we were to connect B and D together and look at the halfway point. They're right on top of each other because they're the same point. Now, looking at this, initially it doesn't look like this has anything to do with vectors. But odds are pretty good this is a vector type question. So we're going to do that. In fact, the hint tells us to use vectors. It says, well, look, suppose you start at A, and you want to get to that midpoint. Well, which midpoint? Well, both midpoints. So let's think about these as vectors. Now, we can either introduce names or we can use points. Now, one thing is we have the vector on this side. I can call this the vector that goes from A to B, or I can give it the name of U. Now, because it's parallel, this opposite side, it's actually the same vector. Similarly, this vector, which is the vector B to C, that's not the same as U, so it's some vector, I'll call it V. That's the same as going from A to D. So this is also V. So when you have parallelograms, you really say, well, the sides are vectors. And so you say, all right, well, so what do we want? Well, if I think about the vector going from A to C, so the vector from A to C, that's the vector U plus V. Now, suppose I want to get to that midpoint, and I start at A. Well, that says, instead of going from A to C, I'm going to go halfway from A to C. So the midpoint of AC, that line segment, can, starting from A, because remember, we want to say how do we get to it, we go 1/2 AC, or if you like, that's 1/2 of U plus V. All right, so that's how we get to the midpoint of AC. Well, that's not so bad. Let's talk about the other midpoint. So let's pick an orientation here. Let's say I'm going BD. So let's talk about BD for just a second here. How can I express that vector in terms of U and V? Because we saw that this A to C was U plus V. What is that? B to D. Well, one thing to look at is we say the following. If we look at this, we have a nice triangle here. And let's note the following. If I go along this edge, that's U. And then I follow immediately by the BD, so U plus BD, I'll end up at D. But that's the same as going from A to D because I have the start and stop A and D. So U plus whatever that side BD is V. Or that side B to D is the same as V minus U. Now we say, that's cool. In fact, we have an idea. So if I want to get to the midpoint of BD, starting from A, there we go. Where do we go? Well, the answer is we first run along that side to get to B. So that's going to be U. And then, now that we're at B, we go halfway from B to D. Halfway there. So 1/2 V minus U. So that would be U plus 1/2 V minus 1/2 U. And now you can see that we can combine the U and the minus 1/2 U. It's this rule here. U minus 1/2 U is 1 minus 1/2 times U. So this becomes 1/2 U plus 1/2 V. And now we say, hey, look, I can apply this rule here. So this is 1/2 times u plus v. And what's the key? Well, starting from A to get to either one of the midpoints, the change is the exact same. So if you have the same start and you have the exact change, you have to have the same stop. And therefore, the center points have to agree. Good. Done.